Hi everyone. Uh, I'm very glad to be here to share our recent research work on a review of deep learning models for spine segmentation. I'm Longfei. Okay, so I will talk about the background and motivation of this work, and also two categories of neural networks, include the UNet family and also the backbone-based models. And then lastly, I will talk about the experimental results. Image segmentation is a very basic question in the field of computer vision. And it is a pixel level image classification method popular in the area of computer vision. It converts input images into areas of interest with highlights. And the medical image segmentation is a long-standing challenge due to some problems like the limitation of label dipsets, the noise, and the artifacts. And as we know, there are some very typical traditional segmentation methods in the field, like the edge detection, the threshold-based segmentation, the region growth method, the cluster-based segmentation methods, and also the activity-based methods. However, there are not that efficient methods in this during these typical methods due to the cumbersome process and the noise effect of medical image equipment. So we need to find some better methods on the medical image segmentation problem. So we're going to use deep learning neural network models, which is a very advanced method. Takes advantage of the very high computational capability of computers and GPUs and new structures of the neural networks. The widely used way in label data process like the semantic segmentation and automatic segmentation performance generally catch up with that of manual segmentations. Okay, so in this work, our goal is to compare the performance of several different kinds of neural networks. And we're going to test these models on the lumbar MRI image segmentation task, and we're going to analyze the possible causes of the differences between the models. And we're going to use a multiple class dataset, which is a lumbar spine MRI dataset with a total of 20 classes, and to evaluate the performance of these networks. And then we finally selected 12 networks, and then we implemented these 12 networks, and we can categorize these networks into two types. One is the UNet family networks, and another category is the model based on backbones. And we compare these networks in this segmentation task on spine MRI. Okay, so then next I will introduce some details about these models. So first, I will introduce the UNet family models. Yeah, first one is the very classic UNet. So UNet has I think this one has become one of the most popular and robust network in the medical image segmentation field, and it has also promoted the emergence of a variety of other variants of this typical UNet. So we can see the structure of this network. It includes basically two parts. The left-hand side is the downsampling, and the right-hand side is the upsampling. And there are connections between the left and the right. We call it skip connections. And some variants of the typical classic U-net include the attention U-net and some others. The attention U-net firstly applied the soft attention technique to a medical image task by using the proposed attention case. As shown here, you can see the details of the attention case. It fused the low-level and high-level information by using ReLU and one-by-one convolution operation and sig mode to focus better on the regions which is needed to be segmented while limited the relevant background regions. The next one is the res U-net. It is similar to the U-net, but the model consists of an encoder and decoder, and each of these has three corresponding blocks. Both SE is the squeeze and the excitation unit. I think this is the big change of the res U-net. Both SE and the attention unit are used to strengthen the ability of the model to capture the representative features and suppress the irrelevant features, especially the background features. Another one is the trans U-net. It's another variant of the classic U-net. This network was proposed by taking advantages of both transformer and U-net. In the encoder, as we can see, the input image goes through CNN to extract low-level information before being sent to the transformer layer to generate global extensional information. And a CUP, which is cascaded upsampler, is introduced in the decoder to upsample the feature map to the full resolution step-by-step. Skip connection is also used in this trans U-net network. Okay, so the next one is the mini SAG, which is also a popular one. So mini SAG is proposed to meet the demand for an efficiency and a lightweight with only 83K parameters. Its most remarkable innovation is the design of the attentive hierarchical spatial pyramid, also called AHSP model. It makes the model focus more on the critical part. I think this is also looks similar to the attention part. And then next, I will introduce some backbone-based models. I think which are a little bit different from the first category, the U-net family. Okay, the first one is the PSP-net, which is designed pyramid polling model, and which called PPM, right? So, and the PPM is inspired by global average polling, which is commonly used in image classification. So the PSP-net network, instead we directly applying global average polling, which might cause information loss. The pyramid polling model was used, and the pyramid polling model used different sizes of convolution kernels to pull the global contextual information extracted by CNN in different subregions before being flattened and concentrated. And the next one is the Deep Lab. It's the version 3 plus. And in the encoder apply the Aurora special pyramid polling, which is also called ASPP module, consisting of several parallel Aurora convolutions with different rates. This module enables the modifiable density of the encoder features, so it can capture multiple scale contextual information. In the decoder, the extracted information is unsampled twice by the factor of 4 to recover more detailed information in this deep lab network. And also the dense ASPP. In this network, the ASPP module has the so there are some disadvantages of the ASPP. For example, it has the problem of missing enormous information, especially when dilated races. And the dense ASPP applies dense connection to the ASPP module to solve this problem. This is the biggest innovation of this network. And also the DA net in this network, the position attention module makes sure similar features at different distances make the same contribution to the final feature maps. And the channel attention module introduced a self-attention mechanism as aggregated features in the channel dimension. And the next one is the EMA net. And the key component in this EMA net is the EMA unit, which is the expectation maximization algorithm. It can obtain a maximum likelihood estimate of parameters by running the AE and AM steps alternatively. AE is used to calculate the attention map expectation, while AM maximizes the data likelihood. And the next one is the InfNet. It's another backbone-based network. This one is inspired by a two-step procedure in clinical practice. Framing the labeling InfNet use the PPD, which is a parallel partial decoder, PPD, to generate a coarse global feature map by aggregating high-level information and then RA modules as a fine labeler, generally erasing the infection region. And the PSA net. And the point-wise special attention network which was called PSA net, was proposed to capture long-range dependence. As we can see the structure in this picture here. The collect and distribute, each of this is used to aggregate the contextual information under the guidance of the attention maps, which connect every position with all the others. And we select the data set, which is include the original MRI lumbar spine image, and also the ground truth images, as we can see on the left-hand side and the right-hand side. And we choose the dice loss as the loss function, and we choose 5 different evaluation metrics, include the dice metrics, the IOU, the false negative rate, the false positive rate, and the recall metrics. And here is the mean results between these different networks. We can see the deep lab and the mini seg has got very good results. The dice loss and the LVU. And here we show some segmentation results visually. We compare the performance between these models. We select 5 MRI images for each model. I think the first two rows are the best one and the worst cases by each model. And then we randomly selected 3 cases, as you can see listed below. Okay, so let's summarize our work here. So we reviewed several models, and we basically we divided them into 2 categories: the UNet family and the backbone-based models. And in this work, we tested these different models with a lumbar spine MRI dataset. And also in this dataset, we have the ground truth labels. And as we can see in the result, the deep lab network achieved best performance among these networks. But the mini seg also achieved a very nice net performance with a very low computational cost. Okay, so thank you.